The warm-up question for today says which shows a transverse wave and then which wave travels faster. And so you have two images down there, A and B, that show different waves in a slinky. Which one of those is transverse, A or B? This goes back to the first day of notes that we did together over waves. What do you think, Mason? A. Yeah, your transverse wave is the one where it's what you traditionally think of as a wave, where you have your crests and your troughs. So A is your transverse wave. Which one travels faster? B. Okay, wave B. That was also in our notes, but I just wanted to again go back to that because it was just one little slide that mentioned it. So please make sure that if you don't have it written down already, you might also want to write that down. Your longitudinal waves are faster than your transverse waves in these mediums. So you may want to make a note of that. But go ahead and make sure that you also have answered this in MyOpenMath so that you get credit for your warm-up today. We are getting closer to your test, which is next week on May 1st, which is next Wednesday. So just a heads up, we're getting closer. If you're trying to study over the weekend, you may want to open up that unit summary and work through some of those problems. Yes, ma'am?
Is the next unit the last unit?
Yes.
What is it?
Light. Light waves. All right. Today we are going to talk about sound and the Doppler effect, among other things, just some properties of sound. And then you're going to have an assignment. This one's a little bit different because it has videos in there that are going to review some of those things with you. Again, we're going to talk about most of it anyway in class, but there are video clips in the assignment that you can watch to help you answer the questions after each one. Everything that's in the questions is in the videos, so if you don't get it from the notes, it'll be in the video clips. If we've talked about these oscillations of waves and strings. We were talking about it yesterday when we talked about standing waves. And like a guitar string, for example, does oscillate and produce transverse waves or standing waves in the string. But the sound that is produced is longitudinal. So although the string vibrates, it's just the same thing over and over again. They've messed with the frame rate so you can see those waves in the strings. But the strings themselves do have those crests and troughs and those standing waves that we were looking at yesterday, and you can see the vibrations in them. But sound is longitudinal. Okay, and so when we talk about the sound that goes from that string to our ear, that is going to be a longitudinal wave. And again, we're talking about sound waves today. So let's go ahead and get to our notes. Okay, so sound is a mechanical wave that results from the back and forth vibration of the particles of the medium through which the sound wave is moving. And this is how a sound wave would propagate outward from a source, like a speaker. If it's playing music, it's going to propagate outward kind of radially in three-dimensional space as well. Of course, I'm just representing this on a flat screen, but spherically, really. But it's these compressions of the air molecules, and that's what's represented by those dots right there that send these pulses outward from that source. But again, it's a longitudinal wave. It propagates outward in all directions, 360 degrees from the source, and it is the result of collisions between the particles, specifically those air molecules that are going to carry the sound wave from the source, whatever it may be, to your eardrum eventually so that you hear it. Again, we talked about mechanical waves versus electromagnetic waves earlier on in our notes. Sound, of course, is a mechanical wave. That does mean that it requires a medium. It does have to have air molecules in order to collide, in order to transfer that energy and transfer that sound. So you can't have sound in the absence of air. So in space, no sound. Okay, so if you see a movie where there's sounds of things in space, then you know that that one's not exactly accurate. But anyway, it is a mechanical wave, and it is a longitudinal mechanical wave that does propagate outward, and it would have an appearance something like this if you were able to see it. Again, if you pick any one of these particles, and I've highlighted like 2 different air molecules here. You can see it's just back and forth motion. The wave's propagating, in this case of this one right here, it's propagating to the left, but the particles, again, aren't moving. So the particles aren't transferred, the matter isn't transferred by the wave, it's just the energy that's transferred. We talked about it kind of like a domino effect, transfer of energy. And pick any particle, they're all doing this. Okay, this one is doing the same thing. And so although you see the wave propagating across the screen, again, in different directions, but over here to the left, the particles themselves are just oscillating back and forth. That is a property of your longitudinal wave. So again, sound waves consist of a repeating pattern of high and low pressure regions moving through a medium. Thus, sound is also called a pressure wave. Your ear is able to detect fluctuations in pressure as the sound wave strikes the eardrum. So you can actually plot the data for pressure within a column of air for a longitudinal wave, and you would get a graph that looks like this: an area of high pressure, an area of low pressure, high pressure, low pressure, and it would actually produce a transverse wave. We did look at that whenever we were talking about types of interference, and we tried to look at 2 longitudinal waves, and I said, hey, if you can't tell what parts this is, you can draw this on top of it. Okay, because that is what's happening if you were to think of the regions of pressure, high and low. You could draw in just a normal looking transverse wave to help you see that. But again, the actual sound wave itself is longitudinal, and it does look more like this image up here. Because sound propagates due to collisions between particles, factors that affect collisions will determine the speed of sound. Thus, and this might seem counterintuitive to you, sound travels fastest in solids, then liquids, then gases. Okay, and it's all about the particle arrangement in those materials. There's a domino effect thing going on right here, and you can see it's kind of trying to represent the different spacing between the particles of the different media. Okay, for a solid, your particles are really close together. And if you watch that domino effect, it's the one at the top here in gray. Because they're so close together, one of them will hit the next one, okay, almost instantaneously. Whereas your liquid particles are just slightly farther apart, not really a lot. Okay, and so that's what's represented here is a little bit farther apart. And this is obviously an oversimplification because your gas molecules are actually much farther away than that. But again, this is an analogy to help you see that. So the gas molecules, because they're farther apart, are going to take longer to collide and thus take longer to transfer that sound. Did you have a question?
If they move faster, why does it like distort the sound?
Because although it is the moving faster, there's also more collisions with everything else in there, and so some of that energy does get absorbed in each of those collisions, and so the sound does end up sounding more distorted, and it doesn't necessarily travel as far because it is absorbed by the medium in solids and in liquids more quickly than in gases. But it is faster. The second factor that affects the speed of sound is temperature. Within a given medium, sound travels faster at warmer temperatures, and again, think of collisions. Like if you have a hotter gas, the particles are moving faster, okay, and therefore they are going to collide faster. And so at higher temperatures, you're going to have faster collisions and thus faster propagation of sound than you would at a colder temperature. Okay, so again, temperature is the second factor that affects speed of sound. Sound does not travel the same in, let's say, Antarctica as it does in Arizona. The speed of sound is going to be different depending on the temperature. Now, is it vastly different? No, not really, but it is different. It is a noticeable difference. Yes, sir.
Why would cold air not be faster? Because the air is denser. So wouldn't it be
It's not significantly so. It's more about the speeds of the particles due to and you're looking at the collisions because that's what actually transfers the energy. All right, so it says, think about it. During a movie, a spaceship explodes as it is flying through space. The audience sees the flames of the explosion and seconds after hears the thunderous sound of the explosion. Exciting scene, no? What is wrong with the physics of this scene? Yes, Kelly?
You wouldn't hear anything.
You wouldn't hear anything. I mentioned that a second ago. Okay, sound cannot travel in a vacuum. Mechanical waves, which include sound waves, require a medium. So if you're in space and you're watching a movie and you see that, not exactly accurate. Okay, so again, make sure that you're aware of that. That's why I guess this movie had this catch slogan, whatever. In space, no one can hear you scream. I don't know if y'all saw Alien. It's kind of old now, but anyway. But yes, that is accurate. If you are in the vacuum of space, there is no sound wave propagation. All right, explain why, as a result of a distant explosion, an observer senses a ground tremor and then hears the explosion. Why would you feel it before you hear it, potentially?
Sound takes time to travel.
Okay.
The wave of the explosion is faster than the wave of sound.
Okay, the wave of the, what do you mean?
Wait, are we talking about like in space?
No, just on Earth, not in space. We had another one? Yeah.
It travels through the solid faster.
There you go. Travels through the solid faster than it does through the air. Okay, and so both of them are both of those would be longitudinal waves. Okay, traveling either through a solid medium or through air. Okay, and you would feel it because it's traveling through the solid before you hear it when it's traveling through the air. Okay, so again, longitudinal waves travel faster in solids like the ground than through air, so the explosion would be felt before it would be heard. So again, we're just applying these different things, and it's all real world stuff. So I mean, I hope you guys aren't near any explosions, but if you are, that would be what you would experience. I guess maybe you go into some field where that's something you do. All right, so properties of sound. First term that we're going to talk about, amplitude. We obviously have already discussed amplitude, but now we're going to discuss it as it applies to sound waves. Okay, so amplitude, again, is the maximum amount of displacement of a particle on the medium from its rest position. For a wave, it tells us how much energy the wave has. We already know that. We wrote it on the board. Energy is directly proportional to amplitude squared, and that's going to apply to sound waves as well. For sound, the amplitude is going to tell us how loud that wave is. So you can see my two birds. One of them is apparently psychotic. But you have a much larger amplitude in this one down here, which just means he's a lot louder. They could be making the same pitched sound and everything else, but if it's louder, you're going to have a greater amplitude than something quiet. Okay, and this is the pressure graph again. It says pressure of a gas. But again, amplitude is volume or loudness for sound. Okay, so again, add that to your notes. Amplitude is the volume or the loudness of the sound. Greater amplitudes means louder sound. Smaller amplitudes mean quieter sound. Frequency. Okay, frequency, again, we've defined it already, but just as a reminder, some of you still needed help with this yesterday in your assignment, but frequency of a wave refers to how often the particles of the medium vibrate when the wave passes through the medium. It is wave cycles per second. Okay, so cycles per time, again, typically in seconds. But for sound waves, the frequency of the wave tells us the pitch. How high pitched is it versus how low is that pitch? Okay, so again, you can see some examples up here, but this red wave at the top of my image is a low frequency wave. There are very few wave cycles per second, assuming that each of these are traveling the same velocity. And so this would have a low pitch to it, something like booming sound of thunder, versus a mouse's high-pitched squeak is going to be higher frequency. And so you can see that there are more of those per second, again, assuming that these are both traveling the same speed. And then something in between, I don't know, pick anything. Our voices, for example, would fall between those two, and they might look something like this. But again, frequency of sound tells you pitch, how high or low. So if we look at an image like this, and this is the type of question you're going to see, which is loudest and has the highest pitch? Okay, yeah, F. I know that it's loudest because it's the tallest. Now, it's the same as E and theoretically A, although A may be a little bit shorter. But it's the same as E. However, that just means they're the same loudness. Okay, the amplitudes are the same. But the highest pitch is going to be the most frequency, so it's going to be the one that looks the most compressed because there are the most cycles per second. So yes, F would be the highest pitched and loudest at the same time. It does appear to have the same or a similar pitch to both B and C, but again, B and C aren't as loud. Okay, so F is the answer you would pick here. An oscilloscope is a tool that helps us visualize waveforms. I do have a link here that we can look at sound waves, assuming that it still works. But it lets us see how that sound wave will look. And you can actually talk into it. So I put this here more for you guys to look at. This is slide 106. Let's see if it's still a good link. I'm hoping it is. It is. Let's see if we can see what, there it is. You can see my voice on the screen as I'm speaking. You can see the sound waves. You guys can play with it. You can sing into it or open a tone generator or something like that. You can try those different pitches and see how the frequency compares. It's linked in slide 106. So if you want to play with that, that might be a fun thing for you to look at. But again, you need it on live input, which I had it on. It says to try humming a constant tone and click freeze live input, and then you can kind of see the wave because it'll freeze it in space so that it's not moving constantly. All right, so Doppler effect. The Doppler effect is observed whenever the wave source, or whatever is making the sound, is moving with respect to an observer. Okay, sounds moving towards the observer will seem higher in pitch than they actually are. Sounds moving away from the observer will seem lower in pitch than they actually are. So their frequencies will appear to be higher or lower than they actually are because of their relative motion to one another. So this is what I mean by that. It's a lot easier to see whenever you're looking at an example. So I have a sound source here that's represented by a black dot, and as it's moving toward this girl, the sound waves in front of it, it's making the waves, but it's also moving toward the wave it just made. Okay, and so the waves end up compressed on this side, and they end up stretched out over here for the same reason. It's moving away from the wave that it just made, so it's a little bit farther away, and then it makes another one, and it gets a little bit farther away. And so you end up with this apparent change in the pitch of the sound. Now, the sound source itself isn't actually changing whatever pitch it's making, but it sounds as if it is. Okay, and so that's the Doppler effect. Wave fronts ahead of the object are compressed, creating an apparent increase in frequency or pitch. Behind the object, the wave fronts are spread out and the pitch sounds lower. So like if you've ever been sitting at like a train track and you hear like a train blow the horn as it's approaching, the sound as it's approaching, it sounds as if it's getting higher, and then after it passes, it sounds as if it's getting lower. Now, the train itself is not changing the sound it makes, but it sounds that way to you because it's moving. Okay, so that's the Doppler effect. So I have a video clip on that and on sonic booms and stuff like that. So I'm going to show you this clip, and then we can talk a little bit more about it.
Humans have been fascinated with speed for ages. The history of human progress is one of ever-increasing velocity, and one of the most important achievements in this historical race was the breaking of the sound barrier. Not long after the first successful airplane flights, pilots were eager to push their planes to go faster and faster. But as they did so, increased turbulence and large forces on the plane prevented them from accelerating further. Some tried to circumvent the problem through risky dives, often with tragic results. Finally, in 1947, design improvements such as a movable horizontal stabilizer, the all-moving tail, allowed an American military pilot named Chuck Yeager to fly the Bell X-1 aircraft at 1,127 kilometers per hour, becoming the first person to break the sound barrier and travel faster than the speed of sound. The Bell X-1 was the first of many supersonic aircraft to follow, with later designs reaching speeds over Mach 3. Aircraft traveling at supersonic speed create a shockwave with a thunder-like noise known as a sonic boom, which can cause distress to people and animals below, or even damage buildings. For this reason, scientists around the world have been looking at sonic booms, trying to predict their path in the atmosphere, where they will land, and how loud they will be. To better understand how scientists study sonic booms, let's start with some basics of sound. Imagine throwing a small stone in a still pond. What do you see? The stone causes waves to travel in the water at the same speed in every direction. These circles that keep growing in radius are called wave fronts. Similarly, even though we cannot see it, a stationary sound source, like a home stereo, creates sound waves traveling outward. The speed of the waves depends on factors like the altitude and temperature of the air they move through. At sea level, sound travels at about 1,225 kilometers per hour. But instead of circles on a two-dimensional surface, the wave fronts are now concentric spheres, with the sound traveling along rays perpendicular to these waves. Now imagine a moving sound source, such as a train whistle. As the source keeps moving in a certain direction, the successive waves in front of it will become bunched closer together. This greater wave frequency is the cause of the famous Doppler effect, where approaching objects sound higher pitched. But as long as the source is moving slower than the sound waves themselves, they will remain nested within each other. It's when an object goes supersonic, moving faster than the sound it makes, that the picture changes dramatically. As it overtakes sound waves it has emitted, while generating new ones from its current position, the waves are forced together, forming a Mach cone. No sound is heard as it approaches an observer, because the object is traveling faster than the sound it produces. Only after the object has passed will the observer hear the sonic boom. Where the Mach cone meets the ground, it forms a hyperbola, leaving a trail known as the boom carpet as it travels forward. This makes it possible to determine the area affected by a sonic boom. What about figuring out how strong a sonic boom will be? This involves solving the famous Navier-Stokes equations to find the variation of pressure in the air due to the supersonic aircraft flying through it. This results in the pressure signature known as the N wave. What does this shape mean? Well, the sonic boom occurs when there is a sudden change in pressure, and the N wave involves two booms, one for the initial pressure rise at the aircraft's nose, and another for when the tail passes and the pressure suddenly returns to normal. This causes a double boom, but it is usually heard as a single boom by human ears. In practice, computer models using these principles can often predict the location and intensity of sonic booms for given atmospheric conditions and flight trajectories, and there is ongoing research to mitigate their effects. In the meantime, supersonic flight over land remains prohibited. So are sonic booms a recent creation? Not exactly. While we try to find ways to silence them, a few other animals have been using sonic booms to their advantage. The gigantic Diplodocus may have been capable of cracking its tail faster than sound, at over 1,200 kilometers per hour, possibly to deter predators. Some types of shrimp can also create a similar shockwave underwater, stunning or even killing prey at a distance with just a snap of their oversized claw. So while we humans have made great progress in our relentless pursuit of speed, it turns out that nature was there first.
So again, you saw the Doppler effect in there, as he was also talking about the sonic boom. So again, you're going to have other videos to watch in the assignment today, so you can look at those too. But just to kind of recap, sound is a mechanical longitudinal wave, so it's got areas of compression and areas of rarefaction. Like all mechanical waves, it requires a medium made up of atoms, some kind of matter, to propagate and transfer energy. Sound travels differently in different media depending on density, temperature, and or state of matter. Properties of sound like pitch and volume are determined by the characteristics of a sound wave. And the frequency of a wave and the amplitude of a wave contribute to its sound. Again, frequency is pitch, amplitude is volume or loudness. Okay, if you're comparing it to light, again, sound is mechanical and longitudinal. It requires a medium. Its energy is determined by its amplitude, and it travels at 343 meters per second in air at room temperature. Light, on the other hand, is electromagnetic, does not require a medium. Its energy is determined by frequency. We're going to talk more about that later in our next unit, and it travels much faster at 2.99 times 10 to the 8th meters per second. Technically that's in a vacuum, but I think it's also in air because I don't think it makes that much of a difference. But again, sound versus light, you are going to have questions comparing light to mechanical waves, and oftentimes that's going to be specifically sound waves. Again, in both cases, energy is transferred, not matter. Those particles of the sound wave just oscillate back and forth. For light, it's an oscillation of electric and magnetic fields. We saw that earlier on a different day's notes. But it's not transferring matter in either case. All right, guys, for the rest of the period, you have the assignment 1303, Sound Videos CFU. You can watch the videos and complete the problem set, and if you don't finish it in class, you can finish it at home. It's due by 11:59 p.m. However, it is in there as a CFU, which means that you cannot retry the questions for credit because all the answers are in the videos that are in there. We've also already answered them in class, or at least most of them. So you should be good, but if you want to make sure that you're good and that you're getting full credit, I would recommend looking at the videos first before you answer the questions. If you have any questions for me, please let me know. And again, I would work on this. You're welcome to work together if you would like.